Right now, as you settle in and let your eyes adjust to the dark, I want you to picture something with me. Imagine you are standing on a beach at midnight. The sand is cool beneath your feet. The ocean stretches out in front of you, black and limitless, and you cannot tell where the water ends and the sky begins. Every direction you look, there is more darkness, more distance, more of something you cannot quite name. You feel small, not in a bad way, just truthfully, irreversibly small. And now multiply that feeling by about 100 trillion, because that beach, that ocean, that entire planet you are standing on is less than a speck of dust in the actual cosmos. And the question we are going to spend the next few hours answering is one that has haunted human beings since the first person looked up at a sky full of stars and wondered where it all stops. Do we live on the edge of the universe? It sounds like a simple question, the kind of thing a kid might ask from the back seat of a car on a long drive. But it is, in fact, one of the deepest, most disorienting questions you can pose to modern physics. Because the answer forces you to reconsider everything you think you know about distance, about direction, about what it means for something to have a boundary at all. And it turns out, the universe has been messing with us. It has been giving us clues for centuries, but those clues point in directions that our brains, frankly, were never designed to follow. So here's what we are going to do. We are going to start where you are, right here, on this little blue marble orbiting an average star in an average galaxy. And then we are going to zoom out, layer by layer, structure by structure, until we reach the very limits of what human beings can observe, measure, and theorize about. Along the way, we will encounter the afterglow of creation itself, confront the strange geometry of space, watch galaxies flee from each other at speeds that defy common sense, and ask whether the universe even has an edge to live on. We will meet the cosmic microwave background, the oldest light in existence. We will wrestle with dark energy, a force so mysterious that it makes up more than 2/3 of everything that exists. Yet nobody can tell you what it actually is. We will trace the architecture of the cosmos, a web of galaxies and emptiness so vast it makes the Milky Way look like a single streetlight in a city that stretches beyond every horizon. And by the end, you will understand not just where we are, but why the question of the edge is far stranger, far more beautiful, and far more unsettling than you ever imagined. There is something else you should know before we dive in. The question of the edge is not just an astronomical curiosity. It strikes at something deeper. It touches on identity, on existence, on our place in the grand scheme of things. For thousands of years, humans believed the Earth was the center of everything. The sun, the moon, the stars, all of them revolved around us. We were the point of the whole exercise. Then Copernicus came along, and Galileo, and Kepler, and Newton, and one by one, they stripped away our centrality. The Earth revolves around the sun, not the other way around. The sun is one star among billions. Our galaxy is one galaxy among trillions. And now, modern cosmology is telling us something even more radical. Not only are we not at the center, but there may not be a center at all. And there may not be an edge either. The universe may simply go on in every direction, without end, without boundary, without limit. That is a hard thought to sit with. Humans are wired for boundaries. We understand rooms and fences and shorelines. The idea of something that just keeps going forever with no end point is genuinely alien to the way our brains evolved. But the universe does not owe us comfort. It owes us nothing. It simply is what it is, and our job, if we choose to accept it, is to understand it as honestly as we can. If you are new here, welcome. If you have been here before, welcome back. Get comfortable, dim the lights, and let the universe do what it does best, blow your mind. Let us begin. Before we can talk about the edge of anything, we need to figure out where we are. And I do not mean your city, your country, or even your continent. I mean your full, honest-to-physics cosmic address. The kind of address that, if the universe had a postal service, would take up the entire envelope. Start with your body. You are a collection of roughly 37 trillion cells, each one performing thousands of chemical reactions every second. Those cells are made of atoms. Those atoms were forged inside the bellies of stars that lived and died billions of years before you were born. The carbon in your muscles, the iron in your blood, the calcium in your bones, all of it was cooked in stellar furnaces at temperatures of millions of degrees, then scattered across space when those stars exploded in violent, luminous deaths we call supernovae. You are, in a very literal and non-poetic sense, made of star stuff. Now zoom out. You live on Earth. The third planet from the Sun, Earth, is about 12,742 kilometers across. That sounds big until you compare it to the Sun, which is about 1.4 million kilometers in diameter, roughly 109 Earths laid side by side. The Sun is one star among an estimated 100 to 400 billion stars in the Milky Way galaxy. Our galaxy is a barred spiral, meaning it has a central bar-shaped structure made of stars with spiral arms winding outward from it. The Milky Way measures roughly 100,000 light-years across. A light-year, for those keeping score, is the distance light travels in 1 year, about 9.46 trillion kilometers. So even at the speed of light, the fastest speed anything in the universe can travel, it would take you 100,000 years just to cross your own galaxy. You would not live to see the other side. Neither would your great-great-grandchildren multiplied by 1,000 generations. But the Milky Way is not alone. It belongs to a small collection of galaxies called the Local Group. This is a modest gathering of more than 50 galaxies, the most prominent being the Milky Way itself and the Andromeda Galaxy, which sits about 2.5 million light-years away. Andromeda is actually heading toward us at roughly 110 kilometers per second, and in about 4.5 billion years, the two galaxies will collide and merge into a single, larger galaxy that some astronomers have already nicknamed Milkomeda. It will be a spectacular cosmic event, though nobody alive today will be around to see it. Zoom out further. The Local Group is part of a larger structure called the Virgo Supercluster, a collection of at least 100 galaxy groups and clusters spanning about 110 million light-years. For decades, astronomers thought the Virgo Supercluster was our ultimate cosmic neighborhood. But in 2014, a team led by astronomer Brent Tully at the University of Hawaii published a groundbreaking study that redefined our address entirely. By mapping the motions of about 8,000 galaxies and tracking their gravitational flows, Tully and his colleagues discovered that the Virgo Supercluster is just one small lobe of a far, far larger structure. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is staggering. It stretches roughly 500 million light-years across and contains approximately 100,000 galaxies with a combined mass of about 100 million billion suns. Within Laniakea, all galaxy motions are directed inward, drawn toward a gravitational center called the Great Attractor, which sits in the direction of the constellation Centaurus. The Great Attractor has been puzzling astronomers since the 1970s, when they first noticed that the Milky Way and many of its neighbors were drifting toward a mysterious point in space. With the mapping of Laniakea, the Great Attractor's role became clearer. It is the gravitational valley floor of our supercluster, the low point toward which everything flows, like water draining into the deepest part of a basin. And here is the detail that matters for our story. The Milky Way does not sit at the center of Laniakea. It sits near the edge. We are out on the outskirts, in the suburbs of our supercluster, perched on a boundary between Laniakea and the neighboring Perseus Pisces supercluster. If Laniakea were a country, we would not be in the capital. We would be in a quiet border town, watching the traffic pass. But even Laniakea is not the end. It is itself part of a still larger structure, the Pisces-Cetus supercluster complex, a galaxy filament, one of the longest and most massive structures ever identified. And that filament is woven into the cosmic web, the grand architecture of the universe, a network of filaments, walls, and vast empty voids that stretches across the observable cosmos in every direction. Picture the universe not as a smooth, uniform sea of galaxies, but as something more like a sponge or the inside of a loaf of bread. Dense threads of galaxies wind through space, connecting massive nodes where galaxy clusters sit. Between those threads are enormous voids, regions hundreds of millions of light years across that are almost completely empty. Almost no galaxies, almost no stars, just darkness and the faintest wisps of hydrogen gas. This is where you live, not at the center of anything, not in any particularly special location, just one small galaxy, on the edge of one supercluster, embedded in one filament of a web that spans the observable universe. Your address, written in full, would look something like this: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Laniakea Supercluster, Pisces-Cetus Supercluster Complex, Observable Universe. And even that last line, Observable Universe, comes with an asterisk, because the observable universe is not the entire universe. It is just the part we can see, the part whose light has had time to reach us since the beginning. Beyond it, there is more, possibly much, much more, possibly infinitely more. And that is where the question of the edge starts to get really interesting. But before we go there, I want you to sit with something for a moment. That address I just described, from Earth all the way up to the Pisces-Cetus supercluster complex, is just the part we know about. Beyond the visible universe, there could be structures so vast they make Laniakea look like a pebble on an infinite beach. We cannot see them. We may never see them, but they are almost certainly there. The universe does not stop just because our telescopes do. There is also the matter of the voids. We tend to focus on the galaxies, the filaments, the bright and busy parts of the cosmos. But the voids deserve attention too, because they represent a different kind of edge. Not the edge of the universe, but the edge of everything we think of as stuff. The Boötes void, discovered in 1981 by astronomer Robert Kirshner and his colleagues, is a roughly spherical region of space about 330 million light-years across that contains almost no galaxies. If you were in the middle of the Boötes void, the nearest galaxy could be more than 100 million light-years away. You would look in every direction and see essentially nothing. Just the faint glow of the CMB and the cold, unimaginable emptiness of intergalactic space. Some voids are even larger. The KBC void, named after Keenan, Barger, and Cowie, who described it in 2013, may be as large as 2 billion light-years across, making it one of the largest known structures in the universe. Some researchers have even suggested that our own galaxy might sit inside or near the edge of this void, which could affect our local measurements of the expansion rate. More on that later. The point is that the universe is not just galaxies and stars. It is also emptiness, vast and structured, sculpted by the same gravitational forces that built the filaments and clusters. The voids are not nothing. They are something. They are a fundamental part of the architecture of the cosmos, as important as the galaxies themselves. When most people hear the phrase, the edge of the universe, they picture something like the edge of a table, or the edge of a cliff, or the border of a map where the cartographer drew sea monsters and wrote, "Here be dragons." Something hard and definite. A wall, maybe. A boundary you could touch, or at least look at, and say, "This is where everything ends, and beyond this, there is nothing. But the universe does not work that way. And understanding why it does not work that way is one of the most important conceptual leaps you can make in all of cosmology. Let us start with a distinction that sounds subtle but changes everything: the difference between the universe and the observable universe. These are not the same thing, and confusing them is the source of almost every misconception people have about cosmic edges and boundaries. The observable universe is the region of space from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. It is a sphere centered on Earth, not because Earth is special, but because we are the ones doing the observing. Every observer, no matter where they are in the cosmos, has their own observable universe, their own sphere of visibility. An alien civilization in a galaxy 3 billion light-years away would have a different observable universe, overlapping with ours, but not identical. Their sphere would be centered on them, and they would see some galaxies we cannot, while missing some that we can. The observable universe has a radius of about 46.5 billion light-years. Now, you might immediately wonder, if the universe is only 13.8 billion years old, how can we see things 46.5 billion light-years away? That seems to violate the speed of light. But it does not, and this is one of those places where the universe plays its best trick on human intuition. The key is that space itself has been expanding since the Big Bang. When light left the most distant objects we can observe, those objects were much closer to us. But during the billions of years that light was traveling toward us, the space between us and those objects was stretching. The light kept moving at the speed of light, as it always does, but the fabric of space was pulling the source farther away even as the light was en route. By the time the light arrived, the source had been carried by the expansion of space to a distance far greater than 13.8 billion light-years. It is like running on a treadmill that is getting longer while you run. You are still moving at the same speed, but the distance you have to cover keeps growing. This expansion is not like an explosion pushing galaxies through space. It is space itself stretching. The galaxies are not flying apart like shrapnel from a bomb. Rather, the space between galaxies is growing, and the galaxies are being carried along for the ride. Einstein's general theory of relativity, published in 1915, predicted this. The equations showed that the universe could not be static. It had to be either expanding or contracting. Einstein himself found this disturbing and introduced a fudge factor called the cosmological constant to try to hold the universe still. He later called that his greatest blunder. But in 1929, the American astronomer Edwin Hubble observed that galaxies are moving away from us, and that the farther away they are, the faster they recede. The universe was expanding. The equations were right all along. Hubble's discovery was itself built on earlier work. In 1912, Vesto Slipher at Lowell Observatory had measured the light from distant nebulae, which we now know were galaxies, and found that their spectral lines were shifted toward the red end of the spectrum. This redshift indicated that the nebulae were moving away from us. By 1925, Hubble had shown that these nebulae were not part of the Milky Way, but were entire galaxies in their own right, located millions of light-years away. And by 1929, he had established a relationship between a galaxy's distance and its recession velocity. The farther away a galaxy is, the faster it recedes. This relationship, now known as Hubble's law, is the observational foundation of expanding universe cosmology. It is one of the most important relationships in all of physics, and it means that the universe is not static, not eternal in its current form, but dynamic, evolving, and expanding. The expansion does not mean that individual galaxies are getting bigger, or that the solar system is expanding, or that the atoms in your body are stretching apart. Gravity, electromagnetism, and the nuclear forces hold bound systems together. The expansion operates only on the largest scales, between galaxy clusters that are not gravitationally bound to each other. It is the space between these unbound systems that is growing. So the observable universe has an edge, a boundary called the cosmic horizon, or sometimes the particle horizon. But this edge is not a physical wall. It is a horizon, much like the horizon you see when you stand on a flat plane or look out over the ocean. The horizon on Earth is just the limit of how far you can see, determined by the curvature of the planet and your height above the surface. There is no wall at the horizon. If you walk toward it, it moves with you, and you see new terrain that was previously hidden. The cosmic horizon works the same way, except it is determined not by the curvature of a planet, but by the age of the universe and the speed of light. There is no wall 46.5 billion light years away. There are almost certainly more galaxies, more stars, more planets out beyond that horizon. Their light simply has not had time to reach us yet. And as each second passes, the observable universe grows a little bigger. New light, from slightly more distant sources, arrives for the first time. Our cosmic horizon creeps outward, and we see a tiny bit more of the cosmos than we did the second before. To put a number on it, the observable universe grows by about 3 light seconds in radius every second. That might sound like a lot, but compared to 46.5 billion light years, it is an infinitesimal advance. We are gaining ground, but the ground is unimaginably vast. In principle, you might think that given enough time, we would eventually see everything. But here is where the universe plays another card. The expansion is accelerating. Space is stretching faster and faster, driven by something we call dark energy. As a result, there are galaxies that are currently receding from us faster than the speed of light. Not because they are traveling through space faster than light, which relativity forbids, but because the space between us is expanding so rapidly that their effective recession speed exceeds light speed. We will never see those galaxies. No signal from them will ever reach us. They are beyond our cosmic horizon not just now, but forever. This creates a peculiar situation. The observable universe is finite and growing, but the accessible universe, the part we could ever reach even in principle, is shrinking. The cosmic event horizon, the boundary beyond which nothing can ever reach us, is not at the same location as the particle horizon, the boundary of what we can currently see. Light from some galaxies has already reached us, so we can observe them, but they are now so far away and receding so fast that we could never reach them with a signal or a spacecraft. We are watching galaxies that are already, in a very real sense, gone. We are seeing their past, but their future is inaccessible to us. They have already slipped beyond the reach of anything we could ever send. This distinction between the observable and the accessible is one of the most philosophically jarring aspects of modern cosmology. We can see things we can never touch. We can know about places we can never visit. And the gap between what we can see and what we can reach is growing every second. This means the observable universe is finite, bounded, and real. But the universe itself, the whole thing, may well be infinite. And if it is infinite, then asking where the edge is makes about as much sense as asking where the edge of the number line is, or where the surface of a sphere ends. The question itself is the problem. Physicist Stephen Hawking used to make this point with a famous analogy. He would say that asking what is north of the North Pole is meaningless, not because the question is stupid, but because the concepts do not apply. The North Pole is the northernmost point. There is nothing more north. In the same way, if the universe is everything that exists, asking what lies outside it is a category error. There is no outside. The universe is not expanding into something. It is just expanding. But wait, if there is no edge, how do we make sense of our earlier observation that we sit on the outskirts of Laniakea, on the boundary of our local supercluster? The answer is that there are different kinds of edges, and we need to be careful about which one we are talking about. There are structural edges, places where one cosmic structure gives way to another. The Milky Way sits on the edge of the Laniakea supercluster the way a coastal town sits on the edge of a continent. There is a real geographic boundary there, but the continent does not end at the coast. There is ocean beyond, and then more land, and then more ocean. The structural edge is not the end of the world. Then there are observational edges, the limits of what we can detect. The cosmic microwave background, which we will discuss in detail shortly, represents the farthest thing we can see with electromagnetic radiation. Beyond it, the universe was opaque, a hot, dense fog of particles that light could not penetrate. We cannot observe anything earlier, at least not with light. It is like trying to see through a wall of fog. You know there is more forest on the other side, but your eyes cannot reach it. And finally, there are hypothetical edges. Some models of the universe suggest it could be finite but unbounded, like the surface of a sphere. A sphere has a finite area, but no edge. An ant walking on the surface of a balloon can walk forever without ever reaching a boundary. It might eventually come back to where it started. Some cosmologists have proposed that the universe could be shaped this way, a three-dimensional version of a sphere's surface, where space curves back on itself in a higher dimension. If this is the case, the universe would be finite in volume, but would have no wall, no boundary, no edge. You could fly a spaceship in one direction forever, and, given enough time and the right geometry, you might end up right back where you started. So when we ask, do we live on the edge of the universe? We need to specify what we mean. Do we live on the structural edge of our local cosmic neighborhood? Yes, arguably we do. The Milky Way sits on the periphery of Laniakea, close to a boundary with neighboring superclusters. Do we live on the observational edge, near the limit of what we can see? No, we are at the center of our own observable universe, by definition. Every observer is at the center of their own observable bubble. Do we live on a physical edge, some wall or boundary beyond which there is nothing? Almost certainly not. No mainstream cosmological model predicts such a thing. But to really understand all of this, we need to go deeper. We need to look at the evidence. And the best place to start is with the oldest light in existence. Let us put some numbers on this, because the numbers themselves tell a story that words alone cannot capture. The observable universe is approximately 93 billion light-years in diameter. That is 93 billion times 9.46 trillion kilometers. If you tried to write that number out in full, in plain kilometers, it would look something like 879 sextillion kilometers. Your brain is not equipped to process that number. Nobody's is. It is a distance so large that every analogy fails. You cannot compare it to anything in human experience because nothing in human experience even comes close. Within this sphere, astronomers estimate there are roughly 2 trillion galaxies. 2 trillion. Each of those galaxies contains anywhere from a few million to several trillion stars. The total number of stars in the observable universe is estimated to be somewhere around 200 billion trillion, or 200 sextillion. That is a 2 followed by 23 zeros. There are more stars in the observable universe than there are grains of sand on every beach on Earth. By a lot. And yet, most of the observable universe is empty. The galaxies, as numerous as they are, occupy a vanishingly small fraction of the total volume. Space is overwhelmingly, devastatingly, almost impossibly empty. If you could teleport to a random location in the observable universe, the odds are overwhelming that you would find yourself in a void between galaxy clusters, surrounded by nothing but the faintest wisps of intergalactic hydrogen and the cold, ancient glow of the cosmic microwave background. You would see no stars. No galaxies would be visible to the naked eye. Just blackness in every direction, stretching to infinity. It would be, in every meaningful sense, the loneliest place imaginable. Now, here is a critical point that is easy to miss. The 93-billion light-year figure is the size of the observable universe today. It is not the distance light has traveled. Light from the most distant objects has been traveling for about 13.8 billion years. But because space has been expanding during that entire journey, the objects that emitted that light are now much farther away than 13.8 billion light years. The light left them when they were close, but the expansion of space has carried them outward. Think of it this way. Imagine you are sending a letter to a friend, but your friend is on a ship that is sailing away from you. You put the letter in a bottle and toss it into the sea. The bottle floats toward the ship, traveling at a constant speed. But the ship is also moving, getting farther away. By the time the bottle arrives, the ship is much farther from shore than it was when you threw the bottle. The distance the bottle traveled is not the same as the current distance to the ship. That is essentially what happens with light in an expanding universe. The expansion also means that the observable universe is growing. As time passes, light from more distant sources has had more time to reach us. Our observable sphere gets a little bigger every second. But because the expansion of the universe is accelerating, there is a limit. Eventually, the expansion will outpace the light. Galaxies currently at the very edge of our observable universe will, in the distant future, be carried beyond the cosmic horizon by the accelerating expansion. We will lose them. Their light will redshift into oblivion, stretching to longer and longer wavelengths until it becomes undetectable. They will fade from view, not because they have been destroyed, but because space itself will have carried them beyond our reach. In the far, far future, trillions of years from now, an astronomer living in whatever civilization exists in our corner of the universe will look out at the sky and see almost nothing. The other galaxies will have receded beyond the horizon. The cosmic microwave background will have cooled to near absolute zero, undetectable by any instrument. The only galaxies visible will be those in our immediate gravitational neighborhood, the ones that long ago merged into a single, enormous elliptical galaxy. That future astronomer will have no evidence that the universe was ever anything other than a single galaxy floating in an infinite, empty void. The evidence of the Big Bang, the evidence of the expanding universe, the evidence of the hundreds of billions of galaxies that once lit up the sky, all of it will have been erased by the relentless expansion of space. The universe will have effectively hidden its own history. That is a sobering thought. We live in a cosmological sweet spot, a brief window of cosmic time when the universe is old enough to have formed complex structures, but young enough that we can still see the evidence of how it all began. A few billion years from now, much of that evidence will be gone forever. There is a famous analogy that cosmologists use to explain the expansion of the universe, and it is worth spending a moment on because it gets at the heart of what makes the observable universe so strange. Imagine a loaf of raisin bread baking in an oven. As the bread rises, the dough expands. Every raisin moves away from every other raisin. If you are sitting on one raisin and looking at the others, you see all of them receding from you. And the farther away a raisin is, the faster it appears to move, because there is more dough between you and that raisin, and all of that dough is expanding. No raisin is at the center. No raisin is at the edge. Every raisin sees the same thing. All the other raisins moving away. This is what happens in our universe. Every galaxy sees every other galaxy, beyond its local group, moving away. The expansion is not happening from a central point. It is happening everywhere, at every point in space, simultaneously. There is no center of the expansion, just as there is no center of the surface of a balloon when you inflate it. Every point on the surface moves away from every other point. The expansion is a property of space itself, not a motion through space. Now, there is a subtle but important consequence of all this that connects directly to our question. If the expansion is happening everywhere at once, and if it has been happening since the beginning, then the most distant objects we can see were not always far away. At the moment the CMB was released, 380,000 years after the Big Bang, the matter that emitted those photons was only about 42 million light-years from the matter that would eventually become us. The entire observable universe, all 93 billion light-years of it today, was once packed into a region only 84 million light-years across. The expansion of space has stretched it to its current enormous size. And this stretching continues every second of every day, in every corner of the cosmos. One more thought before we move on. The observable universe contains a staggering amount of ordinary matter, roughly 1.5 times 10 to the 53rd kilograms. That is about 10 billion trillion kilograms. But ordinary matter is only 5% of the total. The rest is dark matter and dark energy, invisible and mysterious. We are swimming in a sea of unknown substances, and the part we can see, touch, and understand makes up a trivially small fraction of the whole. The universe is not just bigger than we thought. It is stranger than we thought, and the things we cannot see vastly outweigh the things we can. But for now, we have it. And the most important piece of evidence, the one that tells us more about the universe than any other single observation, is the cosmic microwave background. If the universe has a baby picture, the cosmic microwave background is it. In 1965, two radio astronomers at Bell Telephone Laboratories in Homedale, New Jersey, stumbled upon one of the most important discoveries in the history of science entirely by accident. Arno Penzias and Robert Wilson were working with a large horn-shaped antenna, originally built for satellite communications. They were trying to make precise measurements of radio emissions from the Milky Way, but they kept encountering a persistent, low-level noise that they could not explain. The noise came from every direction, day and night, summer and winter. It was not coming from the Earth. It was not coming from the Sun. It was not coming from the Milky Way or any known radio source. It seemed to permeate the entire sky uniformly. They checked their equipment. They rebuilt connections. They even cleaned pigeon droppings out of the antenna, thinking the birds might be the source of the interference. The noise persisted. Meanwhile, just 37 miles away at Princeton University, a group of physicists led by Robert Dick and Jim Peebles were working on a theoretical prediction. They had calculated that if the Big Bang had actually happened, if the universe had really started as an incredibly hot, dense state and expanded outward, then there should be a faint afterglow of that primordial fireball still permeating all of space. The explosion would have produced intense radiation, but as the universe expanded and cooled over billions of years, that radiation would have stretched and cooled along with it, shifting from visible light to infrared and eventually to microwaves. By now, it should be a uniform bath of microwave radiation with a temperature of just a few degrees above absolute zero. When Penzias and Wilson learned about the Princeton team's prediction through a mutual colleague, the pieces fell into place. The annoying noise was not noise at all. It was the echo of the Big Bang. It was the oldest light in the universe, released roughly 380,000 years after the beginning, when the cosmos had cooled enough for electrons to combine with atomic nuclei and form neutral atoms. Before that moment, the universe was a hot, opaque plasma, a seething fog of particles and photons, where light could not travel more than a short distance before being scattered by free electrons. When the electrons combined with nuclei, the fog lifted. The universe became transparent, and the light that had been trapped in that plasma was suddenly free to travel across the cosmos. It has been traveling ever since, for 13.8 billion years, and we detect it today as a faint, uniform glow of microwaves coming from every direction in the sky. Penzias and Wilson won the 1978 Nobel Prize in Physics for their discovery. The Princeton team published their theoretical prediction alongside the Bell Lab's observation, and the cosmic microwave background, or CMB, became one of the most powerful tools in all of cosmology. What makes the CMB so extraordinary is not just that it exists, but what it tells us. When we look at the CMB, we are looking back in time to an era when the universe was only 380,000 years old, a tiny fraction of its current age. We are seeing the universe as it was before any stars had formed, before any galaxies existed, before any of the large-scale structures we see today had taken shape. The CMB is like a wall of light surrounding us in every direction, and beyond that wall, there is nothing we can see with electromagnetic radiation. It is the farthest we can look, the oldest signal we can detect, the edge of transparency. The temperature of the CMB today is 2.725 Kelvin. That is 2.725 degrees above absolute zero, or about minus 270.4 degrees Celsius. It is astonishingly uniform. In every direction you look, the temperature is almost exactly the same, varying by only about 1 part in 100,000. This uniformity tells us something profound. The early universe was incredibly smooth and homogeneous. Matter and energy were distributed almost perfectly evenly across all of space. But those tiny variations, those 1 in 100,000 fluctuations in temperature, are critically important. They represent slight differences in the density of matter in the early universe. Regions that were slightly denser than average had slightly more gravity, which pulled in more matter, which made them denser still. Over billions of years, those tiny seeds of higher density grew into the galaxies, galaxy clusters, and superclusters we see today. The cosmic web, with all its filaments and voids, was imprinted in those minuscule temperature differences in the CMB. The pattern of hot and cold spots in the baby picture of the universe is the blueprint for everything that exists today, including you. Beginning in 1989, NASA launched the Cosmic Background Explorer, or COBE, the first satellite designed to make detailed measurements of the CMB. COBE confirmed that the CMB had a perfect blackbody spectrum, exactly matching the prediction of the Big Bang Theory, and it detected the tiny temperature fluctuations for the first time. The principal investigator, John Mather, and his colleague George Smoot won the 2006 Nobel Prize for this work. In 2001, NASA followed up with the Wilkinson Microwave Anisotropy Probe, or WMAP, which made much more detailed maps of the CMB, pinning down the age of the universe to 13.77 billion years and measuring the curvature of space to within 0.4% of flat. In 2009, the European Space Agency launched the Planck satellite, which produced the most precise CMB map to date, confirming and refining the WMAP results. These measurements have given us an astonishingly detailed census of the universe. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the total mass energy of the cosmos. Dark matter, a mysterious substance that interacts with ordinary matter only through gravity, makes up about 27%. And the remaining 68% is dark energy, the enigmatic force driving the accelerating expansion of the universe. We live in a cosmos dominated by things we cannot see and do not understand. Let me linger on the CMB for just a moment longer, because it is that important. The fact that we can detect this radiation at all is extraordinary. It has been traveling for 13.8 billion years. It has been stretched by the expansion of space from the visible spectrum all the way into the microwave region. It has been cooling all that time, losing energy with every passing epoch. And yet it is still there, filling every cubic centimeter of space, a faint but measurable whisper from the birth of the cosmos. There are about 411 cmb photons in every cubic centimeter of space. You are bathing in them right now. Roughly 1% of the static on an old analog television, the kind your grandparents had, was caused by cmb photons hitting the antenna. You were literally watching the afterglow of creation mixed in with the snow. The CMB also encodes information about the sound waves that rippled through the early universe. Before the fog lifted at 380,000 years, the hot plasma of the early universe was oscillating. Regions of higher density would compress under gravity, heat up, and then bounce back outward, driven by radiation pressure. These oscillations created sound waves that propagated through the cosmic medium at about half the speed of light. When the universe became transparent, those sound waves froze in place, their imprints captured in the pattern of hot and cold spots on the CMB. By analyzing the sizes of those spots, cosmologists can determine the geometry of the universe, the amount of matter it contains, and the rate at which it was expanding when the light was released. The CMB is not just a pretty picture. It is a data goldmine, and it has been the single most informative observation in the history of cosmology. These frozen sound waves also left their mark on the distribution of galaxies. They are called baryon acoustic oscillations, and they show up as a slight excess of galaxy pairs separated by about 500 million light-years. This distance corresponds to the size of the largest sound wave that had time to propagate before the universe became transparent. Astronomers use baryon acoustic oscillations as a standard ruler, a known distance that can be used to measure the expansion of the universe at different epochs. Combined with the CMB, these oscillations provide a powerful cross-check on our cosmological models. The CMB also represents, in a very real sense, the closest thing the observable universe has to an edge. When you look at the CMB, you are looking at the very boundary of what is observable. Beyond it lies the opaque era, the hot plasma of the early universe through which no light could pass. We cannot see beyond the CMB with any form of electromagnetic radiation. It is the wall of first light, the universe's outer curtain, and everything we know about what lies beyond it comes not from observation, but from theory, extrapolation, and mathematical inference. But what can we infer about the overall shape of the space that contains all of this? That question is next. Here is a question that sounds almost philosophical until you realize it has a concrete, measurable answer. What shape is the universe? Not the shape of the observable universe, which is, by definition, a sphere centered on us, but the shape of space itself, the geometry of the cosmos at its very largest scales. This is a question about the curvature of space, and it turns out that the answer determines whether the universe is finite or infinite, whether it has an edge or goes on forever, and ultimately, what its fate will be. To understand cosmic curvature, start with a simpler example. Think about the surface of a sphere, like the Earth. If you draw a triangle on the surface of a sphere, the interior angles add up to more than 180 degrees. This is called positive curvature. A sphere is a finite surface with no edge. An ant walking on the surface of a balloon can walk in any direction forever and never reach a boundary. It might eventually come back to where it started, but it will never fall off an edge. Now think about a saddle shape, like a Pringle chip or a mountain pass. If you draw a triangle on a saddle-shaped surface, the interior angles add up to less than 180 degrees. This is called negative curvature. A saddle-shaped surface extends infinitely in all directions. And finally, think about a flat sheet of paper. Triangles on a flat surface have angles that add up to exactly 180 degrees. Parallel lines stay parallel forever. This is called zero curvature or flat geometry. It is the familiar Euclidean geometry you learned in school. A flat surface, if extended infinitely, goes on forever with no edge. Now, scale this up to 3 dimensions. The universe, at its largest scales, can have one of these 3 geometries: positively curved, like a higher dimensional sphere, negatively curved, like a higher dimensional saddle, or flat. And the geometry depends on one thing: the density of matter and energy in the universe. There is a critical density, a specific amount of mass energy per cubic meter, that determines the geometry. If the actual density of the universe exceeds the critical density, space curves positively. The universe is finite, closed, and will eventually stop expanding and collapse back in on itself in a big crunch. If the actual density is less than the critical density, space curves negatively. The universe is open, infinite, and will expand forever at an ever-increasing rate. And if the actual density is exactly equal to the critical density, space is flat. The universe is infinite, expanding forever, but just barely. So which is it? Astronomers have measured the density of the universe with extraordinary precision, primarily using the cosmic microwave background. NASA's WMAP satellite and the European Space Agency's Planck satellite both measured the matter-energy density of the universe and compared it to the critical density. The result, confirmed by multiple independent measurements, is that the density of the universe is equal to the critical density to an extraordinary degree of precision. The universe is flat, or so close to flat that we cannot measure any curvature at all. The final results from the Planck mission, released in 2018, measured the cosmological curvature parameter to be 0.0007 plus or minus 0.0019. That is consistent with 0, meaning flat. Other measurements, including observations of baryon acoustic oscillations and data from the Atacama Cosmology Telescope, confirm the same finding. The universe, as far as we can tell, is geometrically flat. What does this mean for the question of an edge? A flat universe, in its simplest form, is infinite. It extends forever in all directions. There is no edge, no boundary, no wall. You could travel in any direction at any speed for any amount of time, and you would never reach an end. You would just keep finding more space, more galaxies, more cosmic web, more of the same. But there is a wrinkle. A flat universe could also be finite if it has a non-trivial topology. Imagine taking a flat sheet of paper and rolling it into a cylinder, then bending the cylinder into a donut. The surface of the donut is flat in the mathematical sense, zero curvature, but it is finite. If you walk far enough in one direction, you come back to where you started. Some cosmologists have explored the possibility that the universe has this kind of topology, a flat geometry that wraps around on itself. If that were the case, we might see the same galaxy in multiple directions, because light from it would have had time to travel around the universe and reach us from different angles. Astronomers have looked for this signature in the CMB and have not found it. A 2012 analysis of WMAP data placed a lower bound on the diameter of the universe if it wraps around, at about 91 billion light-years, roughly the size of the observable universe itself. This means that even if the universe does wrap around, it is so large that we cannot detect the effect. The practical upshot is this: the observable universe is a sphere 93 billion light-years across, embedded in a larger universe that is either infinite or so vastly larger than our observable sphere that it might as well be infinite. The Planck data, combined with the theory of cosmic inflation, suggests that if the universe is finite, it is at least 250 times larger in diameter than what we can see. And if it is infinite, then there is no edge at all. Let me put that in perspective. The observable universe, all 93 billion light-years of it, contains roughly 2 trillion galaxies, and 200 sextillion stars. If the total universe is 250 times larger in diameter, then its volume is roughly 15 million times the volume of the observable universe. That would mean there are something like 30 quadrillion galaxies out there, most of which we will never see. And that is the conservative estimate. If the universe is truly infinite, the number of galaxies is also infinite. The number of stars is infinite. The number of planets is infinite. And somewhere out there, statistics being what they are, there might be another planet exactly like Earth, with another version of your city and your street and your house. The laws of probability, applied to infinite space, produce results that border on the surreal. This is not mysticism. This is mathematics. In an infinite universe with a finite number of possible configurations of matter, every possible configuration must occur somewhere. It is the same logic that says if you shuffle a deck of cards enough times, you will eventually get the same order twice. If the universe is infinite and matter is distributed randomly on large scales, then sufficiently far away, beyond any horizon we can ever reach, there is a region of space with the same arrangement of atoms as this one. An exact copy. This is sometimes called the cosmic doppelganger argument, and while it is speculative and unverifiable, it follows directly from the mathematics of infinity and the cosmological principle. Of course, we cannot test this. We can only observe our little patch. And within our little patch, the universe appears flat, uniform, and without edge. Now, you might be wondering, if the universe started with the Big Bang, which happened at a single moment in time, does that not mean it started as something finite? Does that not mean it has a boundary somewhere? The answer, counterintuitively, is no. The Big Bang was not an explosion that happened at one point in space and expanded outward into empty space. The Big Bang happened everywhere at once. It was not matter flying apart from a central point. It was space itself being created and stretching. Every point in the universe was the center of the Big Bang. Every point in the universe is equally old. There was no outside for the bang to happen in. The universe did not expand into something. It just expanded. If the universe started as infinite, it is still infinite, just bigger. Infinity stretched is still infinity. If it started as finite but unbounded, like the surface of a sphere, it is still finite but unbounded, just larger. Either way, there is no edge for you to stand on and look outward into the void. But this raises perhaps the most profound question in all of cosmology. If we are not special, if our corner of the universe is not different from any other corner, then how do we know? What is the evidence that we are not at the center of everything, or at some privileged location near a boundary? That evidence comes from one of the most important principles in all of science. Before you get offended by that subheading, let me be clear, I am not special either. Neither is the Sun, nor the Milky Way, nor the Laniakea supercluster, nor any other object or location in the cosmos. And the reason we know this is one of the most powerful and, frankly, humbling ideas in the history of human thought. It starts with Copernicus. In the 16th century, the Polish astronomer Nicholas Copernicus proposed that the Earth was not the center of the universe. It orbited the Sun like the other planets. This was heresy at the time, not just to the Church, but to common sense. After all, the ground beneath your feet does not feel like it is moving. The sky rotates overhead in a steady, predictable pattern. Everything about human experience suggests that we are standing still and the cosmos is revolving around us. Copernicus said no. We are just one planet among many, orbiting one star among many. We are not at the center of anything. Over the centuries that followed, science delivered one Copernican demotion after another. The Sun turned out not to be at the center of the Milky Way. It is about 2/3 of the way out from the galactic center, in a relatively unremarkable spiral arm. The Milky Way turned out not to be the only galaxy. there are trillions of others. Our galaxy is not at the center of the local group, or the Virgo supercluster, or Laniakea, or the observable universe as a whole. At every level of organization, we keep discovering that our location is ordinary, unremarkable, and in no way privileged. This realization was eventually formalized into what cosmologists call the cosmological principle. It states, simply, that when viewed on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that the universe looks roughly the same everywhere. Isotropic means it looks roughly the same in every direction. Together, these two properties mean that there is no special place in the universe and no special direction. If you were to pick up the entire Earth, along with the Milky Way and everything else, and teleport it to some random location a few billion light years away, the universe around you would look statistically the same. Different individual galaxies, different specific structures, but the same overall character. The same density of matter, the same types of galaxies, the same cosmic web, the same background radiation. The strongest evidence for the cosmological principle comes from the cosmic microwave background itself. The CMB is remarkably uniform. It looks almost identical in every direction, with temperature variations of only 1 part in 100,000. This tells us that the universe was very nearly the same everywhere when it was only 380,000 years old. And if it was the same everywhere then, it should be roughly the same everywhere now, modulo the local variations introduced by gravity over the intervening 13.8 billion years. Galaxy surveys provide further confirmation. When astronomers map the positions of millions of galaxies across the sky, the resulting picture shows that on scales larger than a few 100 million light years, the distribution of matter is remarkably smooth. There are no preferred directions, no unexplained concentrations, no voids that are anomalously large or dense. The cosmic web looks the same in every direction when you zoom out far enough. This is not just an aesthetic observation. It has profound implications for our question about the edge. If the universe is homogeneous and isotropic, then it cannot have an edge. An edge would be a special place, a boundary where conditions change. It would violate the cosmological principle. If you were standing at the edge, you would look inward and see the rest of the universe, and outward and see nothing, or something different. That asymmetry would make the edge a very special, very non-generic place. The cosmological principle rules this out. There are some caveats. The cosmological principle applies on very large scales, hundreds of millions of light years and up. On smaller scales, the universe is obviously not homogeneous. It has galaxies, stars, planets, mountains, oceans, and people, all of which represent dramatic departures from uniformity. But these are local fluctuations, like the ripples on the surface of an otherwise smooth lake. When you average over large enough areas, the ripples cancel out, and the lake is flat. Recently, some astronomers have raised questions about whether the cosmological principle holds at the very largest scales. In 2024, a team at the University of Central Lancashire discovered a structure called the Big Ring, a ring of galaxies 1.3 billion light-years across, located about 9.2 billion light-years from Earth. Combined with earlier discoveries of the Sloan Great Wall, the Hercules Corona Borealis Great Wall, and other enormous structures, some researchers have questioned whether the universe is truly homogeneous at all scales. If structures exist that are larger than 1 billion light years, that would seem to push against the assumption that everything smooths out at a certain scale. However, statistical analyses have generally shown that these large structures do not necessarily violate the cosmological principle. They may be rare fluctuations within an otherwise homogeneous distribution, much like how a single very tall wave does not mean the ocean is not, on average, flat. The debate continues, but the consensus among cosmologists remains that the cosmological principle holds to a very good approximation. And the consequences of that principle are clear. We do not live in a special place. The universe has no center and no edge. Every location is as ordinary as every other. If that sounds deflating, it should not. Because embedded in that very ordinariness is one of the most breathtaking discoveries in all of science. The laws of physics are the same everywhere. The same gravity that pulls your feet to the floor holds galaxies together billions of light years away. The same nuclear physics that powers our sun fuels stars at the edge of the observable universe. The same chemistry that produces water on Earth produces water in interstellar space. The universality of physical law is what makes the cosmos knowable. It is what allows us, from our ordinary little planet in our ordinary little galaxy, to deduce the composition, history, and fate of the entire universe. We are not special, but the fact that we can know this, the fact that we can figure it out from here, is about as special as anything gets. There is a deeper philosophical dimension to the cosmological principle that is worth pausing on. For most of human history, people assumed the cosmos was built for us. The stars were lights hung in the sky for our benefit. The Earth was the stage, and humanity was the play. The Copernican revolution and every scientific discovery since has been a slow, systematic demolition of that assumption. We are not the audience. We are not even the actors. We are a chemical reaction happening on a grain of sand in an ocean so large that the word large loses all meaning. And yet, the cosmological principle gives us something in return for our demotion. It gives us universality. Because we are not special, the physics we discover here applies everywhere. The hydrogen atom on Earth is the same as the hydrogen atom in a galaxy 10 billion light-years away. The law of gravity that keeps your feet on the floor is the same law that shapes galaxy clusters at the far end of the observable universe. The speed of light is the same in every direction, in every location, at every time. This universality is what makes science possible on a cosmic scale. If we were special, if our corner of the universe obeyed different rules, we could not extrapolate from our observations to the rest of the cosmos. But because the cosmological principle holds, our little patch of the universe is a reliable sample of the whole. This is why the cosmic microwave background is so powerful. It is a snapshot of the universe when it was young, taken from every direction simultaneously. And its near-perfect uniformity tells us that the universe was the same everywhere, to extraordinary precision, at a time when the structures we see today had not yet formed. The seeds of galaxies were there, encoded in tiny temperature fluctuations, but the overall character of the cosmos was the same in every direction. No special places, no preferred locations, just physics operating uniformly across all of space. Some scientists have pushed the cosmological principle even further, proposing what is sometimes called the perfect cosmological principle, which adds the requirement that the universe looks the same not just in every direction and every location, but at every time. This was the basis of the steady-state model, proposed by Fred Hoyle, Hermann Bondi, and Thomas Gold in 1948, which held that the universe has always existed and will always exist in roughly the same form, with new matter being continuously created to keep the density constant as space expands. The steady-state model was elegant and philosophically appealing, but it was wrong. The discovery of the CMB in 1965 was a death blow because the CMB is evidence that the universe was once much hotter and denser than it is today. The universe is not the same at every time. It has a history. It has evolved. And that evolution, from the hot, dense Big Bang to the cold, sparse cosmos we see today, is one of the greatest stories that science has ever told. For most of the 20th century, cosmologists assumed that the expansion of the universe was slowing down. This made intuitive sense. Gravity is attractive. Every piece of matter in the cosmos pulls on every other piece. Over billions of years, all that mutual gravitational attraction should act like a cosmic brake, gradually decelerating the expansion. The big question was not whether the expansion was slowing, but by how much. Was it slowing enough to eventually stop and reverse, leading to a big crunch? Or was it just barely slowing? So the universe would expand forever, but at an ever-decreasing rate? In 1998, two independent teams of astronomers set out to answer this question. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees, were both studying a particular type of stellar explosion called a Type 1a supernova. These explosions are remarkably useful for cosmology because they all have roughly the same intrinsic brightness. They are what astronomers call standard candles. Because you know how bright they actually are, you can compare that to how bright they appear from Earth and calculate how far away they are. By measuring the distances and recession velocities of many distant Type 1a supernovae, the teams hoped to map the expansion history of the universe and determine how much it had decelerated. What they found was the opposite of what anyone expected. The distant supernovae were dimmer than they should have been, not brighter, as they would be if the expansion were decelerating, but dimmer, which meant the supernovae were farther away than expected. The expansion of the universe was not slowing down. It was speeding up. The universe was accelerating. This was, without exaggeration, one of the most shocking discoveries in the history of astronomy. It was like dropping a ball and watching it fall upward. It violated every expectation built on decades of cosmological reasoning, and it demanded an explanation. The explanation, or rather the placeholder for an explanation, is dark energy. Whatever is driving the accelerating expansion, scientists gave it this name, a deliberate echo of dark matter, the other great invisible component of the cosmos. Dark energy accounts for approximately 68% of the total mass energy of the universe. It is by far the dominant component, and yet we have almost no idea what it is. The simplest explanation is that dark energy is a property of space itself. Einstein's equations of general relativity allow for a term called the cosmological constant, which represents a constant energy density that fills space uniformly. Even empty space has energy, and as the universe expands, more space is created, bringing more energy with it. This energy exerts a kind of repulsive gravitational effect, pushing space apart faster and faster. If the cosmological constant is responsible for dark energy, then the acceleration will continue forever, driving galaxies apart, stretching the cosmic web, and eventually isolating every gravitationally bound structure in an ever colder, ever emptier void. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for their discovery. It remains one of the most consequential findings in all of cosmology. There is an irony here worth savoring. When Einstein first applied his equations of general relativity to the universe in 1917, he found that they predicted an expanding or contracting cosmos. This disturbed him because, like most physicists of his era, he assumed the universe was static and eternal. So he added a term to his equations, the cosmological constant, specifically designed to counterbalance gravity and hold the universe still. When Hubble discovered the expansion in 1929, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. But now, 7 decades later, the cosmological constant has been resurrected. It turns out that space does have an intrinsic energy, and it does push the universe apart. Einstein was wrong to call it a blunder. He was right for the wrong reasons, and wrong for the right reasons, and the universe, as usual, had the last laugh. The energy density of dark energy is absurdly small by the standards of particle physics. It corresponds to roughly the energy equivalent of a few protons per cubic meter of space. That is almost nothing. But space is enormous, and there is a lot of it. When you add up that tiny energy density across the entire volume of the observable universe, it accounts for more than 2/3 of everything that exists. Dark energy is the most abundant substance in the cosmos, and it is also the most dilute. It is everywhere and almost nowhere, all at the same time. One of the most puzzling aspects of dark energy is what physicists call the cosmological constant problem. When theorists try to calculate the energy of empty space using quantum field theory, they get a number that is about 120 orders of magnitude too large. That is 10 to the 120th, a 1 followed by 120 zeros, times bigger than the observed value. This is, by some measures, the worst prediction in the history of physics. Clearly, something is missing from our understanding, some mechanism that cancels out the enormous quantum vacuum energy and leaves only the tiny residue that we observe. Nobody knows what that mechanism is. It is one of the great unsolved problems of modern physics. For the question of the edge, dark energy has staggering implications. If the expansion is accelerating, then the observable universe is not just growing. It is growing at an increasing rate. But the cosmic horizon is growing more slowly. As a result, galaxies that are now on the edge of our observable universe will, over time, be pushed beyond our horizon by the expanding space. We will lose them. They will vanish from our sky, not because they are being destroyed, but because space is carrying them away faster than their light can travel back to us. In other words, dark energy is shrinking the accessible universe. The total amount of cosmos that we can ever reach, ever communicate with, or ever observe is decreasing. Right now, we can see galaxies as far as 46.5 billion light-years away. But there is another horizon, sometimes called the cosmic event horizon, beyond which galaxies are already receding faster than light. That horizon sits at roughly 16 billion light-years. Any galaxy beyond that distance is already unreachable. We can see its light because the light was emitted long ago when the galaxy was closer, but we could never send a signal or a spacecraft that would arrive. The future reachable universe is significantly smaller than the current observable universe. Dark energy is also the primary reason many cosmologists now believe the universe is spatially infinite, or at least enormously larger than what we can see. Because if dark energy is a cosmological constant, and if the universe is flat, then the most natural, simplest mathematical models describe a universe that goes on forever. The cosmological constant fills all of space uniformly, and there is no mechanism to create a boundary or an edge. But there is something deeply unsettling about dark energy, beyond the fact that we do not know what it is. In late 2024 and into 2025, results from the Dark Energy Spectroscopic Instrument, or DESI, began to suggest that dark energy might not be constant after all. The data hinted that the density of dark energy may be changing over time, that the cosmological constant may not be constant. If confirmed, this would be a seismic shift in cosmology, potentially overturning the standard model and opening the door to entirely new physics. Some researchers have even suggested that the expansion may already be beginning to decelerate, which would have profound implications for the fate of the universe. The coming decade of observations from the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, and the European Space Agency's Euclid mission will be critical for settling this question. For now, what we know is this: the expansion is accelerating, the universe is being pulled apart, and the cosmos we can see is slowly disappearing over the horizon. If there is an edge to the universe, dark energy is making sure we never find it. Let me paint a picture of what dark energy means for the far future of the cosmos, because it is one of the most hauntingly beautiful conclusions of modern physics. If dark energy continues to operate as a cosmological constant, then in about 100 billion years, every galaxy beyond our local gravitational cluster will have been carried beyond the cosmic horizon by the accelerating expansion. The sky will go dark, not suddenly, but gradually, galaxy by galaxy, as each one fades to red and then disappears entirely. The CMB will cool to an undetectable whisper. The light from the Big Bang, the first and oldest signal in the cosmos, will be stretched to wavelengths so long that no conceivable instrument could detect it. The very evidence that the universe was born, that it expanded, that it was once full of billions of galaxies, will have been erased. A civilization born in that era, 100 billion years from now, would look out at a sky containing only the stars of its own supergalaxy, the merged remnant of the Milky Way and Andromeda, and the rest of the local group. Beyond that, they would see nothing. They would have no way to discover the expanding universe, no way to detect the CMB, no way to know that the cosmos was once teeming with galaxies in every direction. Their cosmology would be fundamentally wrong, not because they were bad scientists, but because the universe had hidden its own story behind the expanding horizon. They would be brilliant, curious, and utterly misled. We, sitting here at this particular moment in cosmic history, have access to information that future civilizations will not. That is a strange kind of privilege, and it is one more reason to pay attention to the sky, right now, while we still can. Some theorists have explored even more extreme fates. If dark energy is not a cosmological constant, but instead grows stronger over time, a scenario described by a parameter called the equation of state, then the expansion could become so violent that it tears apart not just galaxies, but stars, planets, atoms, and even the fabric of space-time itself. This is called the Big Rip, and in the most extreme models, it could happen in as little as 22 billion years. In a Big Rip scenario, the universe does not just expand forever. It explodes from the inside out, at every scale simultaneously. First, galaxy clusters fly apart, then galaxies, then solar systems, then planets, then atoms, then the quarks inside the atoms. And finally, space-time itself is ripped to shreds. Nothing survives. The universe ends not with a whimper, but with a rip. Whether the Big Rip will actually happen depends on the nature of dark energy, which remains one of the biggest unknowns in physics. Most observations currently favor a cosmological constant, which leads to a gentler fate, an ever-expanding, ever-cooling cosmos that fades to black over trillions of years. But the DESI results and other recent data have introduced genuine uncertainty. The fate of the universe is not yet decided, or rather, it was decided long ago by the laws of physics. We just have not figured out what those laws say yet. If you could somehow step outside the universe and look back at it, as if it were a snow globe sitting on a shelf, what would you see? You would not see a smooth, uniform distribution of galaxies scattered randomly through space. You would see structure, immense, intricate, bewildering structure. You would see a network of glowing filaments stretching across hundreds of millions of light years, connecting at nodes where massive galaxy clusters sit like spiders at the junctions of a web. Between those filaments, you would see enormous dark voids, nearly empty regions that can span more than 100 million light years. The whole thing would look like a cosmic sponge, or perhaps the neural network of some unimaginably vast brain. This is the cosmic web, and it is the largest coherent pattern of structure in the known universe. The cosmic web is not random. Its architecture was determined by the tiny density fluctuations in the early universe, the same fluctuations that show up as hot and cold spots in the cosmic microwave background. Regions that were slightly denser than average attracted more matter through gravity, growing denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier. Over billions of years, gravity amplified these tiny initial differences into the vast structures we see today. Understanding how this happened requires appreciating the role of dark matter, which makes up about 85% of all matter in the universe. Dark matter does not interact with light, so it is invisible, but it does have mass, and therefore gravity. In the early universe, dark matter began to clump together first, pulled by its own gravity into a scaffolding of halos and filaments. Ordinary matter, which was initially coupled to the radiation field and could not collapse freely, eventually fell into the gravitational wells created by dark matter after the universe became transparent at 380,000 years. This is why the cosmic web is sometimes described as being built on a dark matter skeleton. The galaxies we see are like lights decorating a dark framework that is itself invisible. Computer simulations of this process, such as the Illustris simulation and the Millennium simulation, have produced remarkably detailed models of the cosmic web. These simulations start with the observed properties of the early universe, as measured from the CMB, and then evolve the matter forward in time using the laws of gravity and fluid dynamics. The results look strikingly like the real universe, with the same kinds of filaments, nodes, and voids that astronomers observe in galaxy surveys. This agreement between simulation and observation gives cosmologists confidence that they understand the basic mechanisms of structure formation, even if many details remain to be worked out. The process works like this. In the early universe, matter was distributed almost uniformly, but with tiny variations. Gravity pulled matter toward the densest regions. As matter accumulated along lines connecting these dense points, it formed filaments. Where filaments intersected, matter piled up even more, forming the massive galaxy clusters that sit at the nodes of the web. And the regions between filaments, from which matter had been drained away, became the great cosmic voids. Galaxy filaments are the largest known structures in the universe. They can stretch for hundreds of millions of light years, or even more than a billion. The Sloan Great Wall, discovered in 2003, is a filament of galaxies about 1.37 billion light-years long. The Hercules Corona Borealis Great Wall, discovered in 2013, appears to be even larger, stretching roughly 10 billion light-years, though its exact boundaries are debated. These structures are so large that they push against the limits of what the cosmological principle allows. If structures are too large, they suggest the universe is not as homogeneous as the principle demands. So far, statistical analyses suggest these giant structures are still consistent with the standard model, but they represent some of the most extreme departures from uniformity that we have observed. The voids between filaments are equally impressive. The Boötes void, discovered in 1981, spans about 330 million light-years and contains almost no galaxies. Some voids are even larger. Together, the voids make up the majority of the volume of the universe. Most of space is empty, and it is getting emptier as the cosmic web is stretched by the accelerating expansion. Within this web, our Milky Way galaxy sits in a specific, identifiable location. We are part of the local group, which sits in a filament connecting the Virgo cluster to the Fornax cluster. The Virgo cluster is one of the major nodes in our region of the cosmic web, and the local group sits on the outskirts of its gravitational influence. On a larger scale, as we discussed earlier, the Milky Way is on the edge of the Laniakea supercluster, near the boundary between Laniakea and the Perseus-Pisces supercluster. This positioning is not accidental. It reflects the way structure formation works. Galaxies form preferentially along filaments, near nodes, in the densest regions of the cosmic web. But the Milky Way is not in one of the densest regions. It is in a relatively modest part of the web, in a small galaxy group, far from the massive clusters that represent the web's busiest intersections. If the cosmic web is a city, we are in the suburbs. Not the center, not the edge, just a quiet neighborhood with a decent view. But is the cosmic web itself finite? Does the web have an edge? As far as we can tell, no. The cosmic web extends to the very limits of the observable universe, and there is every reason to believe it continues beyond. The patterns of filaments and voids observed in every direction are consistent with a web that extends indefinitely, governed by the same physics and the same initial conditions everywhere. The cosmological principle predicts this, and the observations confirm it, at least within the volume we can see. This is one of the most important realizations in modern cosmology. The universe is not like a room, with walls and a floor and a ceiling. It is more like an infinite ocean, with currents and eddies and waves, but no shore. The cosmic web is the pattern of those currents, and as far as we can tell, it goes on forever. But how did the universe get to be this way? Why is it so large, so flat, so uniform? To answer that, we need to go back to the very beginning, to a fraction of a second after the Big Bang, when something extraordinary happened. Something that inflated the cosmos from a speck smaller than an atom to a size larger than the observable universe in less time than it takes light to cross a proton. The Big Bang theory has been phenomenally successful. It explains the expansion of the universe, the cosmic microwave background, the abundance of light elements like hydrogen and helium, and the formation of large-scale structure. But the original version of the theory had some serious problems. Not problems with the observations, but problems with the initial conditions. The theory described what happened after the bang beautifully, but it said nothing about what caused the bang itself. Worse, it required a set of starting conditions so precisely fine-tuned that they seemed almost miraculous. 3 problems stood out. The first was the flatness problem. As we discussed, the universe is extraordinarily flat. Its density is equal to the critical density to astonishing precision. But the mathematics of the Big Bang tell us that any tiny deviation from flatness in the early universe would have been amplified enormously as the universe expanded. To end up as flat as we observe today, the universe at 1 second old had to be flat to within 1 part in 1,000 trillion. That is an absurdly narrow target. It is like balancing a pencil on its tip and having it remain balanced for 13.8 billion years. Possible, but wildly improbable without some mechanism to ensure it. The second was the horizon problem. The CMB is nearly the same temperature in every direction, which means that every part of the early universe had to be in thermal equilibrium. Every region had to have exchanged enough energy with every other region to reach the same temperature. But in the standard Big Bang model, there was not enough time for this to happen. Regions on opposite sides of the sky are so far apart that light has not had time to travel between them since the beginning. They are causally disconnected. They have never been in contact. And yet they are at the same temperature to 1 part in 100,000. How? The third was the magnetic monopole problem. Grand unified theories of particle physics predicted that the extreme conditions of the early universe should have produced vast numbers of magnetic monopoles, hypothetical particles with only a single magnetic pole. These monopoles should have been common, but none have ever been observed. Where did they all go? In 1980, a young particle physicist named Alan Guth, then working at the Stanford Linear Accelerator Center, proposed a radical solution to all 3 problems at once. He called it cosmic inflation. The idea was simple in concept, but staggering in implication. Guth proposed that in the first tiny fraction of a second after the Big Bang, The universe underwent a period of exponentially rapid expansion. Not the gradual expansion we observe today, but an explosive, runaway stretching of space itself, driven by a bizarre form of energy associated with what physicists call a false vacuum. During inflation, the universe doubled in size roughly every 10 to the minus 37 seconds. That is 10 million trillion trillionths of a second. In that unimaginably brief period, a region of space smaller than an atom was blown up to a size larger than the entire observable universe today. Inflation solves the flatness problem because any curvature the universe might have had before inflation was stretched out to near-perfect flatness. Imagine blowing up a basketball to the size of the Earth. The surface, which was noticeably curved when the ball was small, would appear perfectly flat on a human scale. You could not detect the curvature. Inflation does the same thing to the geometry of space. Whatever the initial curvature was, it was stretched to irrelevance. Inflation solves the horizon problem because the entire observable universe was, before inflation, contained within a tiny region that was in thermal equilibrium. Everything was in contact. Everything was at the same temperature. Then inflation blew that tiny, uniform region up to cosmic scales. The uniformity of the CMB is not a coincidence. It is a memory of the time before inflation, when the entire universe was small enough and old enough for everything to be in equilibrium. And inflation solves the monopole problem because any magnetic monopoles produced before inflation were diluted by the enormous expansion. If you have a fixed number of monopoles in a region of space, and then you expand that space by a factor of at least 10 to the 75th, the monopoles get spread so thin that you would never expect to find one in the observable universe. Goose published his seminal paper in 1981. His original version of the theory had a technical flaw. The inflation would not end smoothly, but this was quickly fixed by Andrei Linde in the Soviet Union and independently by Andreas Albrecht and Paul Steinhardt in the United States. The revised version, known as new inflation and later slow-roll inflation, became the standard model of the very early universe. In 2014, Goose, Linde, and Alexei Starobinsky were awarded the Kavli Prize in Astrophysics for pioneering the theory. The evidence for inflation has grown steadily stronger over the decades. The predictions of inflationary models, particularly the spectrum of tiny density fluctuations that would be imprinted on the CMB, matched the observations beautifully. The Planck satellite's measurements of the CMB power spectrum show 5 distinct peaks in the pattern of temperature fluctuations, and all 5 match the predictions of inflationary theory with remarkable precision. This is not a vague or ambiguous match. It is a detailed, quantitative agreement between a theory about what happened at 10 to the minus 35 seconds and observations of light emitted 380,000 years later. That kind of predictive power is rare in science, and it gives cosmologists tremendous confidence that inflation, or something very much like it, actually happened. But inflation has a consequence that goes far beyond solving the problems of the standard Big Bang. It suggests that the universe is not just big. It is mind-breakingly, incomprehensibly, absurdly enormous. If inflation is correct, and if the pre-inflation region was approximately the size we estimate from particle physics, then the entire universe today is at least 10 to the 23rd times larger than the observable universe. That is a 1 followed by 23 zeros. The observable universe, all 93 billion light-years of it, with its 2 trillion galaxies and 200 sextillion stars, is an infinitesimal fraction of the whole. We are not seeing the tip of the iceberg. We are seeing less than a single atom on the surface of the iceberg. There is a common misconception that inflation was just a faster version of the normal Big Bang expansion. It was not. During inflation, the expansion was exponential, meaning the rate of expansion itself was increasing. In normal expansion, the rate decreases over time as gravity slows things down. During inflation, the opposite happened. Space was expanding so fast that it was creating more space, which then expanded further, which created more space in a runaway cascade. The energy driving this expansion came from the inflating field, a quantum field that permeated all of space and was trapped in a high-energy state called a false vacuum. As long as the field remained in the false vacuum, the expansion continued. When the field decayed to its true vacuum state, the inflation ended, and the energy that had been stored in the field was released as a flood of hot particles, reheating the universe and initiating what we recognize as the hot Big Bang. The physics of the inflating field is speculative. We do not know exactly what the inflating is, or whether it is a single field or many. We do not know the precise shape of its potential energy curve. Different assumptions about these details lead to different predictions, and testing those predictions is one of the major goals of current and future CMB experiments. The search for B-mode polarization in the CMB, a pattern that would be produced by gravitational waves generated during inflation, has been ongoing for years. The BICEP 2 experiment at the South Pole reported a detection in 2014, but it was later shown to be contaminated by dust in our own galaxy. The search continues with improved instruments, and a definitive detection of inflationary gravitational waves would be one of the most important discoveries in physics, confirming that inflation occurred and providing direct evidence of physics at energy scales far beyond the reach of any particle accelerator. And if the universe is that much larger than what we can see, then the question of whether we live on the edge becomes almost meaningless. We are so far from any hypothetical edge, if one exists, that we could never detect it, never reach it, and never observe any effects from it. We are, in every practical sense, embedded in an infinite expanse. But inflation has one more surprise in store, one that takes the question of the edge and launches it into an entirely different dimension. Here is where things get genuinely weird. Bear with me. In most versions of inflationary theory, inflation does not end everywhere at the same time. It ends in some regions, where the false vacuum decays and releases its energy as a hot, dense soup of particles, the beginning of what we would call a Big Bang. But in other regions, the false vacuum persists and continues inflating. Those regions expand exponentially, growing faster than the regions where inflation has ended. And within those still inflating regions, new patches can also undergo the transition, stopping their inflation and producing their own Big Bangs, their own hot soups of particles, their own expanding universes. This is the theory of eternal inflation, and it was developed by Paul Steinhardt in 1983, Alexander Vilenkin shortly after, and elaborated extensively by André Linde in 1986 under the name chaotic inflation. The basic picture is this: once inflation starts, it never completely stops. It ends in pockets, and those pockets become universes like ours, expanding, cooling, forming galaxies and stars and planets. But the inflating background continues forever, producing an endless succession of pocket universes. Our universe is just one bubble in an infinite, ever-expanding foam. This is the inflationary multiverse, and it is not science fiction. It is a direct, almost unavoidable consequence of the same inflationary theory that so successfully explains the CMB, the flatness of space, and the horizon problem. As Alan Guth himself has said, it's hard to build models of inflation that don't lead to a multiverse. Each bubble universe in the multiverse might have different physical properties. The constants of nature, the masses of particles, the strengths of forces, all of these might vary from one bubble to the next, depending on how the false vacuum decayed in each case. Some bubbles might have physics similar to ours. Others might have physics so different that atoms cannot form, stars cannot ignite, and life is impossible. We would inhabit one of the rare bubbles where the physics happens to be compatible with the existence of complex structures and conscious observers. This is sometimes invoked as an explanation for the apparent fine-tuning of our universe, the curious fact that the fundamental constants seem to be set to the precise values needed for life. If there are infinitely many universes with different constants, then it is not surprising that we find ourselves in one where the constants work. But is the multiverse real? This is one of the most contentious questions in modern physics. The multiverse is, by definition, unobservable. We cannot see other bubble universes because they are causally disconnected from us, separated by regions of still inflating space that we can never cross. Some physicists, like Steinhardt, who helped develop eternal inflation in the first place, now argue that the multiverse is a fatal flaw of the theory because it makes the theory untestable. If anything is possible in some universe, then the theory predicts nothing about ours. Others, like Goose and Linda, argue that the multiverse is a natural consequence of our best physics and should be taken seriously even if direct observation is impossible. There have been some attempts to find indirect evidence. If our bubble universe collided with a neighboring bubble in the distant past, it might have left a circular imprint in the CMB, a cold spot, or a pattern of fluctuations that differs from the rest. Cosmologists have searched for such signatures and have not found convincing evidence, though some anomalies in the CMB, like the so-called cold spot in the southern sky, have been tentatively linked to bubble collisions by some researchers. For our question about the edge, the multiverse changes everything. If the multiverse is real, then not only does our universe not have an edge in the conventional sense, but the concept of the universe itself becomes ambiguous. Our observable universe is a tiny patch within our bubble universe, which is itself one of infinitely many bubbles in an eternally inflating background. The edge of our observable universe is just a horizon, not a physical boundary. The edge of our bubble universe, if it has one, is the region where inflation never ended and space is still expanding at an exponential rate. Beyond that, there are other bubbles, other universes, with their own physics and their own observers asking the same questions. The multiverse, if real, is the ultimate answer to the edge question. There is no edge. There are only more universes stretching outward through inflating space forever. The question, what is beyond the edge, is replaced by which universe is next. And the answer is infinitely many, in every direction, for all of eternity. It is worth pausing to appreciate how strange this is. If eternal inflation is correct, then the total amount of stuff in existence is not just large. It is infinite. Not a very large number, actually infinite, and not just infinite in space, but infinite in variety. Every possible arrangement of matter and energy, every possible set of physical constants, every possible history of a universe occurs somewhere in the multiverse. There are universes where gravity is stronger, where atoms cannot form. There are universes where the strong nuclear force is weaker, where stars cannot ignite. There are universes where the cosmological constant is so large that space expands so fast that no structures of any kind can form. And there are universes like ours, where the constants happen to fall within the narrow range that allows for chemistry, biology, and conscious beings who wonder about the edge of the universe. This is sometimes called the anthropic landscape, and it is both philosophically provocative and deeply controversial. Some physicists embrace it as a natural explanation for the apparent fine-tuning of our universe. Others reject it as a surrender of scientific ambition, a retreat from explanation into mere statistical coincidence. The debate is vigorous and ongoing, and it is unlikely to be settled anytime soon. There is one more twist to the multiverse story that deserves mention. In 2014, the BICEP-2 experiment at the South Pole reported the detection of B-mode polarization in the CMB, a specific pattern of light that would have been produced by gravitational waves generated during inflation. If confirmed, this would have been strong evidence for inflation and, by extension, for the multiverse. The announcement generated enormous excitement, but it was later determined that much of the signal was caused by dust within our own Milky Way galaxy, not by primordial gravitational waves. The search continues with improved experiments, including BICEP-3 and the Simons Observatory. A definitive detection of inflationary gravitational waves remains one of the holy grails of modern cosmology. But let us come back down to our own universe for a moment. Because even within the bounds of what we can observe and test, there is a deep mystery that challenges our understanding of how the cosmos works. A crack in the foundation, a tension that refuses to go away. For decades, cosmologists have had a remarkably successful model of the universe. It is called the lambda-CDM model, where lambda stands for the cosmological constant, dark energy, and CDM stands for cold dark matter. This model describes a universe that is 13.8 billion years old, spatially flat, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and expanding at a rate described by the Hubble constant. The model fits the CMB data beautifully. It predicts the large-scale structure of the cosmos with impressive accuracy. It accounts for the accelerating expansion, the abundance of light elements, and the age and composition of the universe. But there is a problem, and it is getting worse. The Hubble constant, usually written as H0, describes how fast the universe is expanding right now. You can measure it in two very different ways. The first way is to look at the early universe, specifically the CMB, and use the lambda-CDM model to calculate what the expansion rate should be today, given the initial conditions 13.8 billion years ago. This method, using data from the Planck satellite, gives a value of about 67.4 kilometers per second per megaparsec. In other words, for every megaparsec of distance, about 3.26 million light-years, galaxies are moving away from us at an additional 67.4 kilometers per second. The second way is to measure the expansion directly by observing objects in the nearby universe and calculating their distances and recession velocities. This is done using the cosmic distance ladder, a chain of techniques that starts with nearby objects whose distances are well known and extends outward to more distant objects. The most precise version of this measurement, led by Adam Rees and the SH0ES team using the Hubble Space Telescope and later the James Webb Space Telescope, gives a value of about 73 kilometers per second per megaparsec. The difference between 67.4 and 73 might not sound like much, but the uncertainties on both measurements have shrunk to the point where the discrepancy is now more than 5 standard deviations, which in statistical terms is extremely significant. This is not a measurement error. Both numbers are precise and well supported by multiple independent lines of evidence, and they disagree. This discrepancy is called the Hubble tension, and it is currently one of the most pressing problems in all of cosmology. The implications are profound. If both measurements are correct, then the lambda-CDM model is incomplete. Something is missing from our understanding of the universe. The early universe, as described by the CMB, predicts a slower expansion rate than what we actually observe in the nearby universe. Something happened between then and now that the model does not account for. What could that something be? Dozens of proposals have been put forward. Some involve new forms of dark energy that change over time. Some invoke exotic particles that existed in the early universe but no longer exist today, sometimes called early dark energy. Some suggest modifications to general relativity itself. Some propose that we live in a local void, a region of lower than average density, which would make nearby galaxies appear to recede faster than the cosmic average. None of these proposals has gained universal acceptance, and many have been constrained or ruled out by subsequent observations. In late 2024 and into 2025, the James Webb Space Telescope provided crucial new data. By observing Cepheid variable stars in distant galaxies with far greater clarity than the Hubble Space Telescope ever could, the Webb telescope confirmed that the distance ladder measurements are not biased by observational errors. The Hubble tension is real, and the SH0ES team reported that the discrepancy persists at a high level of significance. Meanwhile, the DESI experiment, which is mapping the three-dimensional positions of millions of galaxies, has produced results suggesting that dark energy may not behave as a simple cosmological constant. If dark energy's density is changing over time, it could affect the expansion history of the universe in ways that the standard model does not predict. Some analyses even suggest that the universe's expansion may already be beginning to decelerate, which would be a dramatic reversal of the acceleration discovered in 1998. The stakes here cannot be overstated. The Hubble tension is not just a disagreement about a number. It is a crack in the foundation of modern cosmology. If the standard model is wrong, then our understanding of the age, size, composition, and fate of the universe may all need revision. The universe might be slightly younger or slightly older than we think. It might be slightly larger or slightly smaller. Dark energy might be evolving, weakening, or even changing sign. The expansion might slow down, stop, or even reverse. Every one of these possibilities would change our answer to the question of the edge. Some researchers have proposed that the Hubble tension might be explained not by new physics, but by our local environment. If the Milky Way happens to sit inside a large, underdense region, a cosmic void, then the local expansion rate would be faster than the cosmic average. This is the local void hypothesis, and it has some observational support. The KBC void, mentioned earlier, is one candidate. If we are inside this void, it could explain at least part of the discrepancy between local and CMB-based measurements of the Hubble constant. However, a void large enough to explain the full tension would likely violate the cosmological principle, which assumes that our location is not special. The void hypothesis is therefore controversial, and it illustrates how the Hubble tension touches on some of the most fundamental assumptions of cosmology. Other proposals are even more exotic. Some physicists have suggested that the early universe contained a form of early dark energy that boosted the expansion rate shortly after the Big Bang, but then disappeared. Others have proposed modifications to general relativity itself, suggesting that gravity behaves differently at cosmological scales than Einstein predicted. Still others have invoked new types of neutrinos, decaying dark matter, or interactions between dark energy and dark matter. The theoretical landscape is rich and varied, but no single proposal has gained consensus. What is clear is that we are at a crossroads. The Lambda CDM model has served us extraordinarily well for more than 2 decades, but it may be reaching the limits of its explanatory power. The next generation of telescopes and surveys, including the Vera-C, Rubin Observatory, the Nancy Grace Roman Space Telescope, the Euclid mission, and continued observations by DESI, will provide the data needed to either confirm the standard model or overturn it. Either outcome would be thrilling. Confirmation would mean we understand the cosmos better than we thought. Overturning it would mean we are on the cusp of a revolution, a new understanding of the universe that could be as transformative as the discovery of the expanding universe itself. For our question about the edge, the Hubble tension is a reminder that our map of the universe is not finished. The most fundamental parameters of cosmology, the expansion rate, the nature of dark energy, the ultimate fate of the cosmos, are still being refined. If the standard model is incomplete, then our understanding of the size, shape, and boundary of the universe may need to be revised. The edge, if there is one, or the reasons there is not one, may depend on physics we have not yet discovered. And that is, in many ways, the most honest answer to the question we set out to explore. So, do we live on the edge of the universe? Let us take stock of what we have learned. We live on a small rocky planet orbiting an average star in a galaxy of hundreds of billions of stars. That galaxy sits on the outskirts of a supercluster of 100,000 galaxies. That supercluster is woven into a cosmic web of filaments and voids that stretches across the observable universe, which spans 93 billion light-years in diameter and contains an estimated 2 trillion galaxies. Beyond the observable universe, there is more, possibly infinitely more, possibly an entire multiverse of pocket universes bubbling into existence from an eternally inflating background. The observable universe has a boundary, the cosmic horizon, beyond which light has not had time to reach us. But this boundary is not a wall or an edge. It is a limitation of our perspective, like the horizon on the ocean. Beyond it, there are almost certainly more galaxies, more stars, more cosmic web, extending outward in every direction. The universe itself, the totality of everything, almost certainly does not have an edge. The geometry of space is flat to within the precision of our best measurements, and a flat universe extends infinitely in all directions. Even if the universe is finite, which some models allow, it would be unbounded, like the surface of a sphere, with no edge or boundary. You could travel forever and never reach the end. We are not at the center. We are not at the edge. We are just here, in an ordinary part of an extraordinary cosmos. And the fact that we can figure all of this out, from our little planet, using light that has been traveling for billions of years, is one of the most remarkable achievements of the human mind. Think about what we have accomplished. In the span of a single century, we went from not knowing that other galaxies exist to mapping the cosmic web, measuring the curvature of space, detecting the afterglow of the Big Bang, discovering that the expansion of the universe is accelerating, and identifying the dominant components of the cosmos as substances we cannot see or touch. We went from thinking the Milky Way was the entire universe to realizing it is one galaxy among trillions, embedded in a supercluster on the edge of a cosmic web that might stretch to infinity. That is a journey of understanding that would have been inconceivable to any generation before ours. And yet, the journey is far from over. The Hubble tension tells us that our model of the universe is incomplete. Dark energy tells us that the dominant force in the cosmos is a mystery. The multiverse tells us that the universe we see might be a tiny fraction of a much larger reality. Every answer raises more questions. Every discovery reveals more that we do not know. The frontier of the unknown is not shrinking. It is growing, expanding outward at least as fast as the cosmos itself. There is a passage from the writings of Isaac Newton that feels appropriate here. Newton, who discovered the law of universal gravitation and invented calculus, said near the end of his life, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." 3 centuries later, that ocean is still there. We have mapped more of it than Newton could have dreamed, but it remains vast, deep, and full of surprises. The universe does not care about edges. It does not care about centers. It does not care about you or me. It simply is. Vast, ancient, expanding, accelerating, and more beautiful than any single mind can comprehend. But we keep looking, we keep measuring, we keep asking, because that is what we do. That is what makes us human. And the frontier of discovery, the place where the known meets the unknown, is always the most interesting place to be. There is a final thought I want to leave you with, and it is this. The very fact that we can ask whether we live on the edge of the universe, the very fact that we have telescopes and satellites and mathematical models sophisticated enough to even approach the question, is a kind of miracle. Not a supernatural miracle, but a natural one. Out of the primordial hydrogen of the Big Bang, through billions of years of stellar evolution and chemical enrichment and biological complexity, the universe has produced beings who can look back at it and wonder where it ends. The universe has become aware of itself. You are the universe, looking at itself, asking about its own boundaries. You are made of the same atoms that were forged in the first minutes after the Big Bang, the same elements cooked in the cores of dead stars, the same matter that was once part of the hot, opaque plasma that became the CMB. You are the cosmos investigating its own edge. And the answer, as far as we can tell, is that there is no edge. Just more universe, stretching outward forever, in every direction, at every scale. No wall, no boundary, no curtain, just an endless, expanding, accelerating, spectacularly complex, and breathtakingly beautiful cosmos. And you are in it, right now, right here, alive, aware, and wondering. That is not a bad place to be. If you made it this far, thank you for spending this time exploring the cosmos with me. If this journey sparked something in you, a question, a wonder, a sense of awe, then we have done what we set out to do. Hit that like button, subscribe if you have not already, and turn on the notification bell so you never miss a video. I will see you in the next one. Until then, keep looking up. The universe is waiting.